All right, hi mathematicians. I'm going to talk about differential equations. Chapter 1, right? What is a Diffy Q and where is it used? Okay, I have to slant this so I can write better. Here we go. Okay, so a differential equation is any equation with a derivative. Okay, so you've taken a derivative of an unknown function, and so your goal is to find that function. Okay? And that function is going to represent a family of curves unless you know the initial conditions then you'll find a single curve. And we call that a unique solution. Okay? And so examples, I guess, of differential equations are anything that might, you can have a derivative like this, remember? We can have a second derivative. Right? And so this differential equation, if we were given this, right, our goal would be to find what is this function y? Right? That would be your goal. It would be a function y in terms of x. Right? X is on our x-axis in this one. Let me give you, I guess, one more. We have you can write it with those little dots. I think usually maybe in physics and engineering you see little dots. Okay, but these are all differential equations because they have derivatives in them. It's that simple. Okay, and then so order is important throughout the semester. We start by solving first order, and then we go to second order, and then we do higher order. Okay, so that's kind of how this class is organized. And so at the end of this course, I don't expect you to be able to come upon any differential equation and solve it. I do expect you to be able to come upon a differential equation and know how to use your resources to solve it, especially when it comes to higher order. Our choices are more limited, and you might actually just need to estimate it with technology. Okay? Let's give an example of first order, just so we're very explicit about this. dy dx plus ky goes e to the negative t is an example of first order. Second order, of course, is going to be my d squared y dx squared. And we'll give you a third order just for good measure. Okay, these are just examples of differential equations. Why is it a differential equation? Because it has a derivative in it. First order derivative, second order derivative, third order. Okay? All right, let's see. Where do we see differential equations? Everywhere. You see them everywhere. Where do we see differential equations? Everywhere there's a rate of change. So that means spread of infection, population dynamics, when dealing with birth rate, death rate, electric circuits. Some of you will be taking your circuits class this semester and you'll use differential equations. Oh yeah, fluid dynamics. Differential equations all over the place there. Banking, biology. Okay, if you want to, you can just Google things like marine biology, differential equations, and you'll end up with some applications. Okay, so they're really, really important. Let's talk about just parts of differential equations. If I have an a dy dx, this, of course, is my coefficient. Y is my dependent variable. This is what we're trying to find. Okay, and then this x is our independent variable, which you know, right? It's on the x-axis, independent variable. This class is ordinary differential equations. You will also see as ODE. Okay, and what does that mean? That means that we're taking derivatives with respect to one variable. Okay, later on we do need to use partials a little bit, and so actually maybe I'll do a short video on partials. I love partials. Some people hate them. I don't really understand why, but partial derivatives or PDEs are derivatives with respect to more than one variable. But you only take one derivative of a time still, right? So let's just create an equation. 2xy plus 3z minus x squared y squared equals 0. I don't know, I just made something up, right? Actually, let me define this as f of x, y, and z, right? Because it has 3 variables, I'm going to go ahead and put those in there. That's what that means. So let's go ahead and take, I would call the partial of f, and you draw this, I know it's like a 2. It's like this partial of f, and you go with respect to x. Would be, okay, so now I'm going to take the partial of this with respect to x. I'm only taking the derivative with respect to x, and I'm treating everything else as a constant. Okay, so this would end up being 2y plus, this would be a constant, that would be 0 minus 2xy squared. Okay, I'll rewrite this, 2y minus 2xy squared. So the partial of f, the partial derivative of this with respect to x is 2y minus 2xy squared. The partial of this with respect to y, we then treat y as the variable and everything else is a constant. That would be 2x minus 2x squared y. Why? Because here x is considered a constant, so it just becomes 2x. Here, this is a constant, so it just becomes 0. Here, we're going to end up with the 2 in front. Subtract 1 from this, we get negative 2x squared y to the first. And then if I take the partial of this with respect to z, that's just going to equal 3. Okay, so this is your short partial story. Okay, but we're not in this class. We're in this class. We're in ODEs. Okay, so we do have to deal with partials when we use a theorem later on, but overall, that's not what this class is going to be about. Okay?